Share screen. See. Activate your panel. Okay, view, full screen. Hide video panel. Set up professional audio. I don't need professional audio.
We're amateurs here.
Yes. I can sing out of it. We don't need audio. So that's calculus, right? Yes.
I think so, yes.
Yes, that's what I prepared anyway. If it wasn't that. Okay. Yes.
Elementary.
They didn't ask me just that about n to the n over n factorial. They say, the students from engineering say, does that consider trivial that they said? I just had this discussion. Yeah, it's fine. Okay. So which number lecture are we? I don't even remember.
Seven.
Right.
Let's just start from the top.
Yes,
Okay.
lecture one.
You can do control F
Yes.
lecture, maybe there would be some.
You're right. Saying let's go back to the, no, I never said lecture in the entire lecture.
Not meta enough.
Okay, yes. And fine. So you say let's continue from the last sentence, you understand something. And that goes to elementary school. Okay. And so quick recap. We asked about last time, we asked about the limits. Well, where is the question? Oh, this is the question. Oh, right. We asked about the limit of the n root of n factorial over n, which I did, wouldn't it be nice, and make it into the n root of n factorial over n to the power of n, to use the quotient rule, and I say, if the quotient of the sequence underneath the expression, that's what the word I was looking for, the expression underneath the root, if the quotient of the expression underneath the root tends to L, then the root itself tends to L. That's part of the quotient rule. So we try to calculate the limit of the quotient. That's the ratio between the next element of the sequence over the previous element. And eventually we found this expression. The base of the power tends to 1, the power itself tends to infinity, and that's a problematic case. We're not sure what the limit in such a case. And I saw that the inverse of this question is 1 plus 1 to the n in the power of n. And I told you this is we don't know how to solve it yet, and this is very important. And that was kind of an introduction to the next subject. And we continue with another interesting introduction to the next subject, which is, I didn't say no spoilers, the Euler. What?
I think it's correct.
Yeah, right. Because I need to do a capital E. Euler constant E. And again, whether it's interesting or not, that's for you to decide. I very much like it. But I need to tell you that the start is about probability. Probability is not covered within this course, so it won't be in the exam, right? But it's very easy probability. It just gives you such a nice example. Okay. What does it mean that the probability of some event is 1/100.
On average, you will,
So what does it mean on average? If I do it statistically speaking, the probability is 1/100, right? But what you try to say, the first wrong thing that comes to mind, but it is what I meant, right? That comes to mind is that if we will test this event 100 times, it will happen how many times?
once.
About once. But obviously it is false, right? Because it can happen 0 times or the whole 100 times, given some probability. So my question is this,
Okay.
but that is obviously false. Every number is possible with some probability. So again, the probability part is not that important because this is not a course in probability, you will have one. But it's rather simple, right? If I throw the dice 6 times, would every result appear exactly once? No, right? And if I throw the dice 600 times, how many times will I get the result 1? Dice with 6 edges, right? If I throw it 600 times, how many times do you expect the result 1 to appear? 100, right? But it won't be exactly 100, it would be about 100, maybe. Maybe it will be always 6. There is some probability that would happen, right? Okay, so my question is, what is the probability that when throwing the dice 6 times, at least 1 time the result would be 6.
Sense.
So that's the question. Wait. Say the chances for winning the lottery numbers. What numbers? How do I say it? Numbers, Agala. Numbers are chosen, not a winning ticket. Why is that important to me? Because sometimes students tell me, always once one person wins the lottery if you choose the winning ticket. That's not what I'm saying. You choose random numbers, and if someone chose the correct numbers, he's winning. So it could be possible that everyone wins or no one wins. Okay. So what are the chances of winning the lottery, assuming that the probability to guess a winning number is I don't know, 1 out of 1,000,000, and you bought 1,000,000 tickets. the same question, right? With the dice, it's 6 and 6. 1/6, 6 times. Now it's 1/1,000,000, millions times, right? It's a similar question, but the same thing. What do you think the chances are that you will win at least once? Win at least once. I'm buying 1,000,000 lottery tickets. What are the chances that I will win at least once? Yes.
999,000.
Well, before given the mathematical way to calculate it, can you have a guess, a non-formal guess? What do you think the percentage of the chances for winning will be? Just at the top of your mind, 50-50, either you win or you don't. No, that's probability 101. It either happens or not, 50-50. Yes. That's actually what some people say in the COVID, and it was so annoying.
Either you get it or you don't.
Yeah, the results are not accurate, so it's like throwing flipping a coin. But it's not. Probability means something. So can anyone care to venture a guess?
I think,
No, that's not a guess. That's a calculation.
I think that this becomes to take into account either winning one and losing all the rest, or like winning more than one.
Just a number.
So-
What would you think it would be in the area of 50-50, in the area of 99%,
80%.
80%? Okay, anyone else guess the venture?
Is this, you bought 100 tickets and every single ticket?
Million tickets.
Sorry, that's what I'm.
Yeah.
Each had a different number.
Yeah. A million random tickets. Obviously, if you buy the same ticket 1,000,000 times, then you're an idiot, sorry to say, right? Because either you win it or you don't, right? There is very.
50-50.
So yeah, you bought million random number, right?
Is it a result like?
Value too large. So it's like 1,000,000% chance that I'm winning. Okay. So you see why I told you to guess your calculation or not? Okay. Trivially, okay. So fine, I'll live with the 80% that Thomas said. It's not the correct answer, but it's not too far off, to be honest.
Will it be 100%?
No, that's not true. That's not true.
Probability.
Because that's like the mistake, right? You think it ought to be 100%, but obviously it's not, right? There is a chance that you never chose the right number.
So is it like 99%?
No,
But if, is it 10 chances about or
You remember
so
those
there is a
3
million tickets today. So,
like I said, it's not choosing a winning ticket.
No.
It's random numbers.
Okay.
You choose one out of a million tickets for them to win, and then you 6 to drive 2 out of a million, and then now 3 out of a million, so like you got to do that calculation.
No, I don't. I agree that the way I told the question is confusing, because it seems like what does it mean to have 1/1,000,000 chance, right? If you choose one number between 1 and million, and you choose all the numbers between 1 and million, then obviously it would be 100%. It's not what I'm saying. I'm saying it's an experiment that has a 1 out of 1,000,000 chance to win, and you do this experiment 1,000,000 times, right? And I confess that my wording of the problem was a bit
There's a million.
confusing or wrong even. And I'll phrase it. More correctly.
There's a million tickets.
Each ticket has 1/5 times a loss. Chance to win, regardless of any former events. Okay, that's what I mean. So every ticket, you get some kind of random seed and you say winning or not winning, and the chances of winning is 1 to a million, okay? That's the question, I agree with the number of choosing. I won't say number are chosen, random. And decision of win, okay? And the probability to win. Okay, so now it's correct. So we will calculate, and now in very quickly, we'll get back to calculus, not just because of calculating. We will calculate the chance to never win. Why? What is the chance to not win on the first ticket? Yes, 1, 2, 3, 1, 2, 3 out of a million. 1, 2, 3, 1, 2, 3. Do you agree? What are the chances to not win at 2 tickets? That's squared, right? What are the chances of not winning at 1 million tickets? That in the power of 1 million. Agreed? But that could be written, if you see or not, at the form 1 minus 1 million in the power of 1 million. Okay, and now you can see, hopefully, it is very closely related to that, right? How closely related, I will show you. In general, sorry. Yes, but what is this number? That's correct this time. It's about 63%, that's the right number, but why is this? Where does this 63 come from? You will see in a bit. What? Yeah, no. But what? Yeah, there is a very strong clue here about the next subject, right? Yes, and so in general, 1 minus 1 over n to the power of n is equal to n minus 1 over n to the power of n, which is the inverse of n over n minus 1 to the power of n, which is 1, not exactly 1 over, wouldn't it be nice, n minus 1 plus 1 over n minus 1. Do you follow so far the algebra? This is actually calculus, you need to know that stuff. And this is 1 over 1 plus 1 over n minus 1 to the power of n. So that is actually very closely related to this. Right, small difference. Here the power denominator here is n, and in this case the denominator is n minus 1, but that is, as we will prove, negligible. That won't be a big problem. So you get this, and what did I tell you that this tends to? The denominator, we will see that it tends to 1 over e. Okay, and let's just put it in Wolfram for a second. Wolfram 1. So, and I remind you, these are the chances of not winning. the chances to lose every single ticket out of this million is 0.36. And so therefore, 1 minus that is 0.63 are the chances of winning. So it's 1 minus 1 over 8. Right? So the chances of the chances to win at least once are about 1 minus 1 over e, which is about 0.53%. Okay, so that is quite surprising, right? Because we felt the probability means 1 out of a million. It's 1 out of a million, but actually the chances for at least 1 out of a million is just 63%. 36 of the times you won't even get 1 out of the million, right? So just that is something interesting in probability. But the reason I do it, and there is actually one more example that will show you it. We will see that together later when we learn about derivatives. But the reason I do it is to show you how the Euler constant and why is it so important. It just appears in a lot of different questions in different subjects in mathematics. You think this is just a random question, like last time when it was the average of the numbers, E. And now the probability, E. And later it will be what are the derivatives of the logarithm, and E will arise, right? It's a very important constant that appears out of nowhere time and time again. And that's the reason we wish to learn about it, because it's there and it's important. Okay, any questions so far? So that's enough with the introduction. I will just write the bottom line. So we wish to study the limit of the sequence 1 plus 1 over n to the power of n. Does it have a finite limit at all? Right? Maybe it tends to infinity. Maybe it tends to 0. Does it have a finite limit at all? And if so, what can we say about that limit? Okay, so that's the question. Any questions so far? And I'll go back to Wolfram and I'll put here plus. So it's 1 plus 1 over millions in the power of the millions. And what is the result? It says, yeah, so it's 2.71828. And if I'll go to Wolfram and I tell him E, it says, start the same, it has many different, many more digits, right? Infinitely more. Are they the same? No, obviously not, right? Because this number is not E. What would E be? The limit of this sequence, right? So it means that the sequence is getting closer to E, but doesn't have to actually reach it. The way to learn about sequences, okay? About limits. How, assuming the limit is indeed the number E, how can we prove it? What are the problems when proving the limit of this sequence is actually the number E?
It's irrationals.
Wait, what did you say?
We don't know what E.
Yeah, so I like it better. First, we have no idea what the number E, the number E is. And I wish to tell you something about that. For instance, the number pi, what is the number pi? These are the first digits, it's not the entire number, I mean,
The ratio between circumference and the
it
radius.
is half of, is the area, let's go with Euclid, of the unit circle. It's half its circumference, what I usually say, but it's also the area of the unit circle, agreed? That's a very clear definition. It's not clear how do you get from this to 3.14, right? But it's clear what is the definition of pi, agreed? The number square root of 2, what is that? Is the positive solution for x squared equals 2. Agreed? We have a very clear definition for the number. I'm not saying we know the digits, but we know what is the definition of this number. What is E? What?
The sum.
Right? I need some definition. What is its number? Even if I don't know how to calculate it, in order to prove that something tends to something, I need some kind of definition to work with. And in high school, we see the number E, but we never define it. And there is a reason, you will see in a second, because the definition is not as simple as the definition of pi or the definition of square root of 2, right? So we don't know, I won't keep badgering you with it, because we don't learn it in high school. We don't know what the definition is. Actually, we are going to prove that the sequence 1 plus 1 over n to the power of n has a finite limit and define this limit as the number E, exactly. So E is defined to be the limit of the sequence, and in this case, I don't need to prove that the sequence tends to E. I just need to prove that it has some finite limit. And we call that number E. Later, we will prove that E equals 2.71 something. I mean, I will show you the first couple of digits. If we define E to be the limit, I will show you the limit must be 2.71 something. And what is the other special property of E that everyone knows? Yeah, and E to the power of x and the derivative of E to the power of x is E to the power of x, right? So the two things you actually know about E are these two. We will prove them both. I define E as the limit of this sequence, and using that definition, I will prove to you that it's the first couple of digits are this. It has infinite number of digits. I will not show you all of them in this course. Maybe I'll move on to the next one. Kidding. And I will prove to you that the derivative of E to the x is E to the x. Okay, so this is what is important. And I think this part of the introduction is the most important one, because when I think what should we take from the course about the number E, it's this. This is the definition. These are the theorems. And remembering exactly how we proved each thing is not that important, at least for E. In general, I would like you to understand the proof of the theorems because that's calculus, like arithmetics of limits and so on. But actually, the number E is a bit of a detour for a super important constant. So the detour itself is less important for me than what did we define and what did we prove. That is very important for me. Okay? Yes, Evan.
So is Euler's constant that he came up with it
Ah,
2000 years ago?
Euler wasn't 2000 years ago, it was about 400 years ago. Yeah, Euler.
I'm thinking of Euclid.
Yeah, oh, right, not you,
But
so,
Euclid-
exactly right, Euclid came nowhere to Euler constant, because Euler constant came from subjects more closely related to calculus and algebra, and which Euler did.
But Euler came.
But he didn't come up with it, Newton and Leibniz came up with it, because they did derivative. And later, and they actually named the number P or C, something like that, and later came Euler and it was changed to it, so basically it's a thing. No, I'm only kidding because Euler did so much in mathematics, it's understandable even, but ununderstandable would be it's not a word, because it's implausible, I understand. Yeah, so no, I'm not that familiar with Euler, but I did check this out and it wasn't the first to talk about it because it arose naturally when speaking about derivative. So it was known before him. But he came up with, and that we won't see in this course sadly, but he came up with the Euler equation or formula.
Or the
Yeah, equals is theta. And therefore the highly regarded Euler identity e to the I pi plus 1 equals 0. Right, so Euler does deserve a lot of respect in that area, but I will just tell you that the results for this come from calculus, from this time, basically. I can show you in 2 seconds, and I will delete it. E to the I pi derived twice. What is this?
Minus.
Yeah, it's minus e to the I pi, to the ix, I mean, right? Because I squared is minus 1. What kind of function, when you derive it twice, you get to minus the original function?
Cosine.
Cosine and sine. So that's the basic proof behind this thing. You can see it, more nicely, but using Taylor series, you may see it in the second calculus course, but it depends on the lecture. Not everyone show it. I like it very much, so I usually show it. But this is, by the way, ordinary differential equation way to speak about the problem. And I'm delivering. That's really out of the course already. But it follows from the fact that e to the power of x, the derivative to the power of x. Okay, so we need to prove. We need only to prove that the series 1 plus 1 over n to the power of n has a limit without actually finding it as a finite limit, right? But that's weird. Why? But the definition of a limit surprisingly uses the limit, right? The definition is blah blah blah. That's not the formal stuff.
That's how I would put it.
Yeah, Thomas. an minus L, so write it 1 plus 1 over n to the power of n minus e smaller than epsilon, right? But how can I do it when I don't even know the number e yet, because I didn't prove it? How can I prove? How can I prove? How can one prove that a sequence converge? That means have a finite limit and a finite limit without finding it first. So I'll let you give me some answers in a bit, but the question for this answer, the answer for this question will be some kind of theorem that we will write and prove, phrase and prove, and will be important by itself, regardless of E as well. Important as in a question in the test, okay? But that's the question we are dealing with now. How can one prove that the sequence has a limit without being able to calculate it and using the limit definition? Yes, Thomas.
Can we make a sandwich?
You are very correct that the sandwich will be one of the ways. Sandwich in is, and you know that I don't usually write it, is a correct answer in general, but won't help us here. So it's a very correct answer. It is a way to prove that the sequence has a limit without finding it, and sometimes we do it, but we want another tool. And why is sandwich so good? Because I change the sequence and then I'm able to find the limit of another sequence, which I can actually do. Here it won't work because the limit is E. So how can I sandwich it? I still need another sequence that tends to E, and I will remain with the same problem. Yes.
Because these are the
No, not L'Hopital, not by a long shot. L'Hopital uses derivatives. And we wish to prove something about derivatives. So no, not L'Hopital rule as well. L'Hopital again depends on the following proof. So theorem, I will just write the theorem. Excuse me, a definition first. Definition and then theorem definition. A sequence AN is called increasing if for F or monotone increasing or monotonely it doesn't accept it as a word. Or monotone increasing.
monotonic.
Monotonic.
I think.
Yes, I think you're right. Monotonic increasing. If for every n, natural n, it is true that an is smaller or equal to an plus 1. Okay, notice that increasing could be constant. Okay, it's not super important, but it is somewhat important, right? And we define increasing as increasing, or sometimes lecturers call it non-decreasing, but I find it confusing and I simply say increasing, but I remind you that I mean non-decreasing. That the next element is bigger or equal to the former element. Okay, agreed so far? So we have and obviously there is a similar definition for monotonic decreasing. I will not write it as it is a waste of time. So theorem, given an increasing sequence AM, one exactly one of the following holds. One, the sequence AN is bounded and has a finite limit. Two, what is the other option? Obviously, first of all, it's unbounded, and therefore, but what its limit will be? It's increasing and unbounded, and its limit is infinity, exactly. So it can't jump around like -1 to the n when it's -1, 1, because it's monotonic, right? So the only two options, that's not a proof, I'm just saying it for you to understand. So the only two options for a monotonic sequence will be to be bounded and have a finite limit, or being unbounded and tending to infinity. So what do we need to do next? We need to prove this theorem. That's the first thing I'm going to do. And later, we need to prove that this sequence is increasing and bounded. When it's increasing and bounded, then it must have a finite limit, and then I can say the limit is defined to be the constant Euler E. Okay, the number that the sequence has. Okay, any questions so far? And like I said, this theorem, it's not just for the constant Euler E. I always put
Emphasis.
not just emphasis, a question in the test in this subject. And I'm writing it now. A question about this theorem will appear on the test. You can exercise it in questions number 5, it's not Mambo number 5, in the following link. And I will give you that. So just a couple of seconds, MathWiki. And so just look with awe and about the number of tests, more than 40. Each of them, I will open one in randomly. Each of them, question number 5, look, תהי סדרה, let there be a sequence such that for every n, an plus 1 equals to that. And also I tell you that the first number is 3. First, prove that the sequence is monotonic decreasing. Second, find the limit of this sequence. So each question number 5 from this huge list uses that theorem that if it's monotonic and bounded, it has a limit. How exactly does it use it? You have to solve 2 or 3 questions, but as you can see, you can read like 5 solutions even and still have enough exercises to last your lifetime. So, you will use this. And I promise you, that such a question in the following, genre will be, on the test. Okay? It's like 22 points.
Then the deviation will be a near central limit that our quiz is going to be a different date because of the breaks or whatever.
Okay,
So we're not sure yet which quiz is going to be when, we will have 2 on the 22 or 1 in the 22 and 1 in the 29.
so whether it's on the quiz or not, it will be, I can promise you it will be, because I'm teaching it today. But yeah, they will update us all about when will the quiz be, but it will be on the quiz as well. I meant the final test, but the quiz as well. So you can start looking at it now. And you actually don't have to learn anything else because it uses this theorem. You don't need to see how does it go, how do you solve such a question, it's not only yes, but after you do it like 5 times, you get it. And I would probably do at least one example in the lecture as well, but just exercising it is the only way to actually understanding it, and it's one of the first tangible things I can tell you. This is a technique you must know, other than the general, you need to understand it. So, so next we will prove the theorem, and then later we'll get back to the Euler constant, and then I remind you it will be a detour to just to prove algebraically that this sequence is increasing and bounded. It's quite a detour. It uses tricks and magic and nothing you should be able to invent yourself in such a question. It's very hard algebraically because it has a power and it has the variable both in the base of the power and also in the power itself. So algebraically it will be hard, and we will speak about it later. For now, I will prove the general version of the theorem. As I said, it is important by itself, and we are able to prove it. Okay, it's not the magics and tricks. Proof of the theorem. So first, assume AN is bounded, and remember it is increasing. So we know that the sequence AN is increasing, that's the data of the theorem. And we assume firstly that it is bounded, and we wish to prove that the sequence has a finite limit. Next, we will assume that it's unbounded, and we will prove that the limit is infinity. And that gives us exactly one of the two, right? Either it's bounded and therefore has a finite limit, or it's unbounded and therefore the limit is infinity. By the way, a similar theorem holds for decreasing sequences. Either it's bounded from below and therefore has a finite limit, or it's not bounded from below and therefore tends to minus infinity. Okay? So we assume that the sequence is bounded, remember it's increasing, and we wish to prove that it has a finite limit. But in a sense, we got back to square one, or even further back from that. We have a general sequence now, not a specific one like in Euler's constant. We have a general sequence, and we need to prove that it has a limit, and therefore the definition of a limit. But we have no idea what the limit is. Can any of you venture to guess what will be the limit? I have a bounded sequence. What will be the limit of that sequence? But what, right? What is the bound? Right? Because we learned there are infinite bounds.
This is
It's superbound, exactly. We will prove this definitely was
something very similar to this. Probably.
we learn about boundaries. That's yes, when we learn about supremum, we spoke about something similar. Right? We will prove that the limit is L, which equals the supremum of all of the elements of the sequence. Why does the supremum even exist? I mean, not every set has a supremum. Why does this set has a supremum?
Because we are stating that it's bounded.
Because the set is not empty, meaning we have elements in the sequence, and bounded, and the real numbers field is I forgot how to
Uncountable,
what?
uncountable,
No, not uncountable. I should have mentioned it sometime in the course. I don't remember which word I used. And there is probably a correct one which I will look for in a second, but I wish to find where I told you this before. If I didn't, that's important to tell you now. Supremum. Second, maybe I did not do it.
maybe you said we didn't write it.
No, here, given a non-empty set, does it have to be a supremum? No. And in the rational numbers, the answer is no. But in the real number fact, oh, I didn't say what this property is called. That's the way I avoided it. In Hebrew, it says the number is shalem. I'll make sure how you say it in English. I don't remember. Sadeh shalem. No. Complete. Oh, it's complete. Okay.
That's it.
It's complete. Yeah. Definition. It's the definition is without a supremum, sadly. It's equivalent, obviously. You see, they're even mentioning square root of 2 that's missing from the rational numbers, but due to this property, it is within the real numbers. But in any case, is complete, by which we mean that every non-empty bounded set has a supremum. We obviously not proving that the real field is complete because we need to define it correctly, which we won't do. But that's the basic property, that's the basic reason that we did not remain with the rational numbers, that we advanced to the real numbers. And in the real numbers, this property holds. And due to it, we have supremum, and therefore we have a limit, and you will see, like I told you, this theorem is very important. It appears within the proofs of many other theorems. And it uses the fact that the real number field is complete. That's why we can work with it rather than rational numbers. Okay, so we do have a supremum. Before I will continue writing the proof, I want to illustrate it. So this is the supremum L. Where is the entirety of the sequence at?
Before L.
Before L, right? This is the sequence. Okay. Take an area around L. Does the sequence must appear within the blue brackets?
Yes.
Yes, because it's the supremum. If no one of the elements will be here, that means that the left bracket is another upper bound and lesser than L, which contradicts L being the smaller upper bound. Agreed? So there will be, and by the way, what is the number of what is the size or what is the location, position of the left bracket?
L minus epsilon.
Exactly, L minus epsilon in the proof, right? Because we're taking epsilon step back, epsilon step forward. So there will be an element here. I'll call this element A K. Okay. What is it enough to prove that this is the limit? The fact that there is one element there? What do we need to prove in order to prove a limit?
That there's a finite amount of elements that are not within the limit.
Right, so it's not enough that there is one in there, but it's more than infinite amount. That's from some point forward, all of them,
Yeah.
right? But where will be the next elements of the sequence?
Closer to that.
Why?
Because it's increasing.
Basically, exactly. What I said so far was true for any bounded sequence. The fact that it's increasing changes the game because it say, oh, then everyone else are to the right. And never go past L because it's its boundary. So all the elements will remain within this part of the area of L. And that will prove the theorem. So just write it up, but that's actually the proof. That's what we wanted to prove. Okay? So then I think the most powerful thing I did not prove is that the real numbers field is complete. That there always is a supremum, there always is the closer upper bound. And by that I will not prove. I think you can understand it with the fact that in the real numbers you can take infinite amount of digits. So you can think that for every upper bound you can be a bit more exact, right? And if you take the entire infinite sequence of digits, then you get the exact supremum. It's not a proof, but that's the basic idea behind it. Okay, so now I'm going to write some stuff. So given a positive epsilon and since L minus epsilon is smaller than L, then L minus epsilon is not an upper bound of N, since L the least upper bound. Therefore, there exists some element A K in the sequence such that AK is larger than L minus epsilon. Do you agree? Okay, that's exactly what I've shown you in the illustration. Now I'm writing it up exactly. Mathematical and
Sorry, what are you trying to prove here? No, I mean.
the limit of A and Z.
That, like, so we're trying to prove.
So the general, the bounded increasing sequence has a finite limit.
Okay.
The finite limit is the supermoon.
Okay.
So now that's what I'm doing. I'm taking the supermoon, I'm taking an area around the supermoon, I say the entirety of the sequence other than a finite amount of numbers is inside the area. That is literally what I'm doing, right? L is the supermoon, that's important to remember. And that's what we're using here,
Yeah,
because L is the least upper bound.
yeah, no, I'm just saying, like, what's the difference between this and what we proved before about the sequences, on the sequences and limits, because it's
We
increasing.
define, we didn't prove.
How we
Fine, it's the definition of limit that there is no difference. That's the definition of the limit, right? There is a general definition of limits. And now we're proving that in the specific case of an increasing sequence, the limit must be the supermoon. Okay? And now, since AN is increasing, now we used two of the data we have. First, that the sequence is bounded. Now we will use the fact that it's increasing. Since AN is increasing, for every n larger than k, it is true that AN is larger or equal to AK. Agreed? And therefore, or thus, L minus epsilon is smaller than AK. The left blue bracket is smaller than some element of the sequence goes past it, which the rest of the sequence is to the right of. However, which number does AN never pass? L, because it's the boundary, it's the supermoon, which is smaller than L plus epsilon, which is what we needed to prove. And that proves that AN tends to L. It's not the end because we need to attend to the unbounded case, but for the bounded case, we are done. If a monotonic increasing sequence is bounded, its supermoon is its limit. Okay, great. So when I will prove that 1 plus 1 over n to the power of n is increasing and bounded, then it must have a limit. It's a supermoon of the set of elements of the sequence. And when there exists such a supermoon, because they are the real numbers, we can take infinite number of digits and that's most exact. And any questions up until now? Yes, Sam.
Why did you have the L plus epsilon at the very end? Like, is that just to show that it's within the area?
Yeah, that's like the full accurate proof of the definition, right? Because the definition says it's within the area. It's obvious that it's within, like I told you in the illustration. if it's if it is between the left blue bracket and the limit, obviously it's within the area. But to be accurate, I have to prove that it's between L minus epsilon and L plus epsilon, but it's obvious, and that's why I just wrote and notice that L is smaller than L plus
But
epsilon.
it doesn't necessarily have much significance.
Yes, doesn't have at all, because you know, we've proven here that the elements are less than L, they'll never pass L to the right. But this is the accurate proof of the actual definition. Okay?
Because the sequence is increasing, it's not increasing, it's not decreasing.
Yes.
The supremum could be between.
Yeah, it could be a constant. If the supremum is within the sequence, then the sequence will be constant. Because if it reaches the supremum, it's not allowed to go back, and it's not allowed to go forward. So it's just for the constant series, or at least constant from some point forward. So it's not very interesting, but yes, a constant sequence is a specific example to this theorem. It's a stupid one, because the constant obviously has claimed you don't need a theorem. But yeah, it does fit within this frame of the proof. Okay, and so next assume an is unbounded, since it is increasing, it is bounded from below by the first element, and therefore it doesn't have an upper bound. So if I'm saying the sequence is increasing and unbounded, it must be that it's unbounded from above, because it's increasing. From below, it is bounded by the first element, but from above, it is not bounded. Given M, a positive number F, could it be an upper bound?
If we said it's unbounded,
No, it is not an upper bound. And what does it mean that M does not bound the sequence from above?
it's within the sequence.
Not within. We talked about this with sets. We don't like say within the set. It's not true. What does it mean that a number is not larger than every element of the set? There is an element in the set which is larger than M. And therefore, there exists a K such that a K is larger than M. Agreed? If M is not an upper bound, some element of the sequence is larger than M. No matter how large M is, right? If M is a million or a million to the power of million, some element of the set will be larger than him. Correctly? What is this going to prove? You take any number and say the sequence passes it. Yeah, right, that's 10 to infinity. But it's not enough to have one number. What happens after AK?
There is another number.
For all n after k, it is true that
And then it's bigger than x.
therefore it's true that an okay, but an is larger or equal to AK. Why is that true? The sequence is increasing. It is true that AN is larger than AK, which is larger than M. So what did we prove? AN tends to infinity. That's the very definition of infinity, the limit being infinity. For every M, from some point forward, all of the elements of the sequence are larger than M. This is exactly what we proved. Again, using the fact that it's unbounded and increasing. It's bounded and increasing, but it has a finite limit. It needs what they said. If it's bounded and increasing, it has a finite limit. If it's unbounded and increasing, it tends to infinity. So now I can say to you. Yes.
Because you did a bigger equals, don't you need another step to prove its infinity?
No, because it's bigger or equal, but larger than M. Because since M is not an upper bound, there must be an element strictly larger than it, not equal.
Given an arbitrary M, you mean that, right?
Yes, exactly. Because it could be that you imagine in your head that the entirety of AN will be equal to AK, but then it won't be bigger, like you said, than an arbitrary M, right? Because for every M, there is some element bigger than it, and it's enough.
Okay.
That's the reason we define it as larger or equal, because the proof works and we don't have to split it into cases. So it's like the easiest way to reference the whole thing. It works in the general case. Any questions so far up till now? Okay. I don't have a lot of time, so I won't speak about Euler's constant yet. I will give you an example for this kind of question. Example. And say A1 is positive.
But now that we proved that, we can just,
Use it, yes.
well, how we just quickly use it now to show that the thing that we talked about.
No, the problem is to prove that the specific sequence of Euler's constant is increasing and bounded. That's the hard part, actually.
Oh,
Yeah, that's the hard part. Like I said before, the algebra is horrible. Because you have a power and variable in the base and with the power. So it takes some time to do the algebra to prove this increasing and bounded. Both are quite challenging. So that's why I don't have time to do it in 15 minutes. But like I said,
would you use induction?
no, it doesn't work with induction. It's really, you'll see. It's not, you're welcome, more than welcome to try to prove it, really. Because only when you try to prove it, you understand just how horrible it is. Just imagine in your head, like you said induction, right? So this is AN, this is the element. What is AN plus 1? So this becomes n plus 1, and this becomes n plus 1. You change the base and you change the power. You have no algebraic way to make a connection between the two. So no, it doesn't work with the induction at all. It has two known way to prove it. One using Bernoulli's inequality, and the other using the averages theorem. If you know what I'm saying, let's make sure how do you call it in English. That's the way I usually do it.
We didn't see it yet, or?
I mentioned it.
Yeah.
Yes,
And you said.
but I mentioned it like on the side, but we didn't really use it. AMG, that's a horrible name, yeah. But it's algebraic mean and geometric mean. It's the mean theorem, maybe? Or QMA and GMA inequality.
Yes.
Obviously, but you know it.
Don't you ever think about the QMAM? I don't know what's the inequality.
By the way, the simplest case is implicit in Euclid's, Euclid. Okay, so we'll speak about it later, but it is true. I did mention. Oh, I went to Wikipedia instead of MathWiki. Oh, and here. Second, the number E. That's basically the proof that I will show you. You see it has some steps. Also, the second proof. Second proof uses Bernoulli's. Yeah. It's not trivial. Okay, that's it's not trivial. Yeah. Okay. So like I said, I will do it in the next session. Now let's look at the following example. Say an is larger than 0, and for every n, it is true that an plus 1 equals an plus 1 over an. Okay. Again, I need a term in English. Probably recursion.
Yeah, the process sequences.
Yes. Yeah, fine. Okay. And a recursive sequence. And in computer science, basically programming, it's quite clear how to program a recursive function that returns to, or even an iterative one in a for loop that returns to the n elements. You just go over all of the elements and use this formula to calculate the next one. Okay, so that is sometimes the way we give you sequences. Sometimes we give you a direct formula using the index n, like saying an is 1 plus 1 over n to the power of n. But sometimes we give you the next element, a sequence of the next element given the form of one. So for this kind of question, a lot of the times this theorem is the way to go. We don't know what is the sequence exactly, because I did not tell you what is the first element. I just told you that it is positive. So you cannot know exactly what is the sequence, but the question is nevertheless, find and prove the limit of this sequence. So it looks like a bit of a hard thing to do. Let's open the computer for a second, really. Programming, pie chart, yeah. It has all the charm. And let's just do it iteratively. I'll define A to be some positive number. Let's start with 1. Okay. And let's do it like, I don't know, 100 times. And A equals A plus 1 over A. And print A. So it will give me the 100 elements. Let's print it within the loop, so I'll see all the elements. So it went on to 14.21. Let's continue until 10,000 you make. 141. Okay, I'm not sure what is number. What will happen you think if the first element is smaller than 1, say half?
It's the first one is going to be big, but then it's going to the difference is going to become one.
What do you think the limit would be? What is the limit here?
141.
Is that the limit?
No,
The same sequence when we took first 100 elements was 14, 100,000 it was 141, so what? No, there is. What is the limit? The answer, there is no limit, it won't be true, because it's either. Yeah, infinity, because it will be a monotone sequence, and therefore it's either infinity or finite one, so here it's infinity. What do you think will happen when we change the first element to half?
it will still be infinity.
Let's make sure. Basically, even got to the same number. I am a bit surprised about that. Let's start with 0.0001. I guess that would be low. Oh, it might be even higher, to be honest. Wow, it's higher. Why? Because on the first time you add 1 over the elements, right? Yeah, so it didn't really matter in this case, okay? So our experiment, let's just say, gives us the Hanacha assumption, hypothesis, that's the word I was looking for, that the limit is always infinity. The question is how to prove such a thing.
Is it infinity? It's weird. Because the amount it increases is always lower.
What? Not sure. It might depend. I'm not sure because I only have 5 minutes and I wish to prove that. I'm not sure what happens if you start with a negative number, whether it goes always to minus infinity. Is it true though? No, I think it's minus infinity. If you take a negative number, then this is negative and this is negative, and you get just minus the positive case.
If it's less than -1, then yes.
That it doesn't matter.
No, but if it's, for example, -1/2, then the first.
Like I said, take the minus out. You get the minus of the following example. You get simply the minus of the positive number one. It doesn't, yeah.
Stop arguing, let's see it
Yeah.
later.
Yeah, no, I think because I did. Okay, so the proof is quite elegant and fast, and that's why I find it so such an interesting way of thinking about it. First, since A1 is positive, assume by induction that AN is generally positive, that the N, it's not, that N that you are given a case for which the number is positive, and therefore AN plus 1, which is AN plus 1 over AN, is also positive. What did I prove here? Thus, all of the sequence is positive. Why did I do that? Positive. And I know where I'm going with it, to be honest. Now, what is AN plus 1 minus AN?
1 over AN.
1 over AN. What did I just prove? That this is positive, right? So what does it mean that the difference between AN plus 1 and AN is positive? Yeah, exactly. Therefore, AN plus 1.
That doesn't prove the limit.
You're right. That's 3 more minutes. AN plus 1 is larger actually than AN, and the sequence is increasing. What does the theorem prove? The theorem that we proved says, and thus AN has a finite limit or tends to infinity. Agreed? assume, how do we call it, ABS? ABS, assume by, no, ABC, assume by contradiction, yes, it is the card. Assume by contradiction that AN is bounded and tends to a finite limit. Since AN is always larger than the first element or equal to, then L is larger or equal to the first element, which is larger than 0. Now, the limit of AN plus 1 is equal to the limit of AN plus 1 over AN. Because they're equal terms. What is the limit of AN plus 1? If AN tends to L, we learned a theorem that says that AN plus 1 also tends to L, because it's a different only in the first element. What about the right? AN plus 1 over AN. What is its limit?
L plus the limit of. No, L plus L.
Not L, 1 over L. Right? If AN tends to L, then this tends to L, and this tends to L, and this tends to L. Agreed? Therefore, 1 over L equals 0. Contradiction. Okay, and thus AN tends to infinity. We assumed it has a finite limit, we got a contradiction that it tends to infinity. Such an elegant way to prove that it's unbounded. We didn't actually show that the sequence is large, but we did show that it must have a limit and it couldn't be a finite one. So it just had to be infinity. I really like that. That is like the genre of the question number 5 that I told you. It's one example. Sometimes the limit is finite and we find it using this method, right? But that's enough for today. See you on Tuesday, right?
Yeah.
Yeah. No holidays or what.
Wait, when were we finish? No sé, you can't get a massacre on, but.
I think so. We finish. I think we finished at 6, and we're supposed to. I think nothing canceled. I checked it out if I'm not